Hello and welcome to Sefasok Academy The Intellect on YouTube. In this channel, we are out to help the advanced level science students to attain their academic excellence and their academic goals by providing them with the correct and the time-saving approach to all GCE questions as proposed by the GCE board. In this video, we are looking at June 2019 Advanced Level Physics Paper 2, Section A, Question 6, D and F. So before I continue, I would like you guys to subscribe to the channel and activate the notification bell to not miss any of our videos uploaded subsequently. So the question 6 says, that is the Roman 1, define photoelectric effect. Roman 2, state two experimental observations with regards to photoelectric effect which classical physics could not explain. F says a certain element has a work function of 1.90 electron volt. Determine Roman 1, its threshold wavelength. Roman 2, the maximum kinetic energy of the emitted electrons when the element is illuminated by light of wavelength 4.50 times 10 to the negative 7 meters. Roman 3 says the stopping potential of this element. So the E part of the question is talking about experiment, and the experiment, we're not going to do it here. We are just going to concentrate or focus on the calculations. So solution. Roman 1, photoelectric effect is the emission of an electron from a metal surface, from a clean metal surface, when light of sufficiently high frequency hits its surface. So photoelectric effect is the emission of photoelectrons when light of sufficiently high frequency hits a clean metal surface. So if the light is not having a sufficiently high frequency, no electron will be emitted. So Roman 2, they said what photoelectric effect can explain that classical physics could not explain. The first thing is that we can have that the almost immediate emissions of electrons. Classical physics cannot explain the almost immediate emission of electron, because in photoelectric effect, when light of sufficiently hit the metal surface, there is an almost, when they say almost immediate emission of electron, it means that the electron are actually emitted immediately as the metal surface is heated by the light of sufficiently high frequency. So the next is that the emission of the electron does not depend on the intensity. So when they say it does not depend on the intensity, that means that when a light of sufficiently high frequency touches the metal surface, it is a frequency that is responsible to emit the electron. The intensity can be there to increase the number of electrons emitted, but not to initiate the emission. So it's a high frequency that is there to initiate the emission. We can give the 3, we can give the next part, the existence of the threshold frequency. So classical physics cannot explain the existence of the threshold frequency. Now let's solve the F part of the question. They say we should calculate the threshold wavelength. So let's first of all define it. It is a maximum wavelength of incident radiations capable of ejecting photoelectrons from a clean metal surface. It is the maximum wavelength of incident radiations capable of ejecting photoelectrons from a clean metal surface. That is the definition of the threshold wavelength. So we go to the calculation now of the threshold wavelength. We know that the work function WO is equals to HFO, and we also know that HFO, which is the threshold frequency, is equals to the speed of light all over the threshold wavelength. So we make the threshold wavelength a subject of the formula. We're going to have that threshold wavelength is HC all over WO. Now they've given us WO in the question. H is simply the Planck constant, which has value 6.63 times 10 to the negative 34 joules second. C is the speed of light, and it has value 3.0 times 10 to the 8 meters per second. And W0 is given in the question, which is 1.9 US electron volt. So 1 electron volt is 1.6 times 10 to the negative 19. So now multiplying it to the 1.9, we have 1.9 times 1.6 times 10 to the negative 19 joule. So calculating now the threshold wavelength, we just substitute the values into our expression, and we have the threshold wavelength to be 6.54 times 10 to the negative 7 meters. When you punch your calculator properly, you have the answer. So Roman 2, you are calculating the maximum kinetic energy. So the calculating the maximum kinetic energy is from the law of conservation of energy, which says that the energy, that E there stands for the energy of the light. So when light is incident on a clean metal surface, it will first of all set the electrons into motion, and that electron into motion will possess kinetic energy. So plus the work function now, which will emit which the energy required to emit the electron, that is to eject the electrons from the metal surface. So from there we can make Ke max the subject of the formula. We have that Ke max is E minus WO. But now we know that E is equals to H times F. H is the Planck constant and F is the frequency of the light. So we have already calculated the threshold wavelength. It's easy for us to calculate the work function. Now, frequency of the light is speed of sound all over, that is the speed of light all over the wavelength of the radiation. So which is 3.0 times 10 to the 8 all over 4.5 times 10 to the negative 7. It was given in the question, of which you calculate it properly. We have 6.67 times 10 to the 14 per second, or hertz there. So we now calculate the threshold frequency. The threshold frequency is simply the speed of light all over the threshold wavelength, as we have stated when calculating the threshold wavelength. So we have calculated the threshold wavelength. We now calculate the threshold frequency, and we have value as 4.59 times 10 to the 14 per second. So from there we can now calculate the maximum kinetic energy, of which we can factor out the H. We have H into F minus F naught. So we have 6.63 times 10 to the negative 34 into 6.67 times 10 to the 14 minus 4.59 times 10 to the 14. So calculating properly, we have kinetic energy as 1.38 times 10 to the negative 19 joule. So that was that for the maximum kinetic energy. Now Roman 3, the stopping potential of the element. Calculating the stopping potential of the element, we know that the maximum kinetic energy is equal to the electron times the stopping potential. So we have calculated the maximum kinetic energy before. We want to calculate the stopping potential. So the stopping potential is kinetic energy max all over the electric charge there. So we have calculated the kinetic energy, which is 1.38 times 10 to the negative 19 joule all over the electronic charge, which is 1.6 times 10 to the 19 joule. So calculating the stopping potential, we have that Vs is equals to 0.86 volt. So guys, we have come to the end of this video, and I will invite you to like the video, subscribe and share to your friends in the advanced level for them to be able to attain academic excellence. And don't forget that in science, consistency is the key.